Today we're going to talk about regression, which is a statistical technique that we can use to predict a dependent variable or an outcome that we're interested in predicting or measuring based on the level of one or more independent variables or factors that we think might have an influence on that dependent variable. We're going to start off in this video by talking about simple regression, where we have one independent variable and one dependent variable. And then we'll do another one where we talk about multiple regression, where we have multiple independent variables. You can only have one dependent variable or outcome that you're interested in measuring with a regression analysis. And further, that dependent variable has to be quantitative in nature. With your independent variables, you can have as many of them as you want to, and they can be either quantitative or categorical. If they're categorical, though, we have to use either zeros or ones to represent the different categories, the different values. So we'll take a look at an example in the next video that has that as well. For simple regression, let's say that we have a business owner. We'll call him Peter, and Peter has some pizza restaurants. And he's decided that he wants to see if it makes sense for him to advertise on the local radio station. So what he does is he comes up with a graph that measures his weekly sales, and that's on the y-axis. Y is used to designate our dependent variable. And on the x-axis, we're going to measure the number of daily radio ads. That's our independent variable. That's the one that we think may well have an impact on that weekly sales. So what he does a little experiment. Some weeks he does one ad running per day. Some weeks he does two. Some weeks he does three. Some weeks he does four. And he measures the level of weekly sales then that go along with that. And we'll put some gradations here in $5,000 increments for our sales levels. And we'll just plot out what happened here. The first week he ran one ad and he ended up with about $6,000 of sales. And then running two ads the next week he had $8,000, and three ads a day went up to $9,000. Four actually dropped back to about $8,000, but then we had another week of four that was a little bit higher, and a little bit higher here and here and here. And we can then notice that there's a trend. This trend is that as the number of ads per week goes up, let me move this one up just a little bit. As the number of ads per week goes up, the level of sales also goes up. There's a direct relationship, and it essentially follows a pattern of a straight line. All of the dots don't line up exactly on that straight line, but that line is a fairly good representation of the data that we have represented, the relationship between those radio ads and the weekly sales. Well, now Peter decides, well, hey, I learned back in algebra that I could create an equation for that line, and based on that equation then, maybe I could predict what my level of sales would be given a certain number of ads that I choose to run in any given week. So you may well remember that the formula for a straight line is y equals mx plus b, where y is our dependent variable, x represents our independent variable, and in this case, y is the weekly sales, x is the number of radio ads. The m here is our slope of the line. How much does y change by changing one unit of x? And b represents our y-intercept. Now there are a couple of other forms of this equation that are often used and are a little bit more useful in transitioning to regression analysis. You may have also seen y equals a plus b times x. They've shifted the order of the terms over here on the right, and they've shifted the letters that represent the slope and the intercept. But basically it's the same thing. Y is our dependent variable, x is our independent. B, the coefficient that goes along with the independent variable, is the slope, and the coefficient that's all by itself is the y-intercept. So a little bit different order, a little bit different representation, but it means the same thing. In regression analysis, they use slightly different formats, and it depends a little bit on what book you use. Your particular book, we use something called y hat. That stands for the predicted level of y, or our dependent variable, is equal to beta sub 0, which represents the intercept, plus beta sub 1 times x sub 1. And when we get into multiple regression, we'll see that we can extend that out for however many independent variables we have. We could have beta sub 2, x sub 2, beta sub 3, x sub 3, and it could go on and on and on for as many different independent variables as we're interested in looking at. So what regression analysis tries to do is take a set of data points, whether it's represented graphically by points or with just 2 columns of data in a spreadsheet, and generate this type of an equation that we can use to predict that y variable based on the level of x variables. To do this, I'm going to utilize the OJuice data file, which corresponds with problem 11.22, beginning on page 616, and we'll take a look at StatCrunch and see how we can utilize StatCrunch to perform a regression analysis. In this particular example, we have an orange juice producer that is interested in being able to predict the sweetness index. According to federal regulations, sweetness index for particular types of orange juice has to fall within particular parameters, but yet there's no way of knowing what the sweetness index of a particular juice batch is going to be until it's done. So manufacturers try to come up with a way that they can predict that. And they have surmised that perhaps using the pectin levels of the oranges that go into the batch might help us to predict the sweetness level that comes out. Let's run our regression analysis. To do it, we'll go to our Stat button. You'll notice that there's an option here for regression. And since we have just the one independent variable, this is going to be a simple linear regression. It's multiple linear if we have more than one independent variable, and the other 2 options here, polynomial and logistic regression, are beyond what we're doing in this class. So this is simple linear. You'll notice here that we can put in our x variable. That's the independent variable, or the one that we think will have an effect on the other one. In this case, that's going to be our pectin. Our y variable is the dependent one, or the one that we want to predict. It's our outcome. That's our sweetness index. So we put in those for x and y, and there's not really anything else that we need to worry about here. We can just go ahead and click compute and take a look at our results. You can see that our p-value overall for our regression model comes out at 0.0181. That's less than 0.05, so that means that we do have a significant predictive relationship between the pectin levels and the sweetness index, so that's good. And that's really all that we have to worry about with this bottom table, is making sure that that overall p-value comes out to be less than 0.05. It tells us that the pectin is a significant predictor of sweetness. it's these parameter estimates here then for the intercept and the slope that tell us how we can create our equation. And you'll notice up here at the top, they actually have gone ahead and created the equation for us using those parameter estimates, but they carried it out all the way. They're saying that our y variable, or the sweetness index, is equal to 6.252069 minus, because this is a negative sign here, that whole big decimal number there times the pectin level. We may well want to simplify that a little bit. We could say, for example, that our y hat, or our predicted level of sweetness, is going to be equal to 6.25 or 6.252 minus 0.0023 multiplied by the pectin level. Once we have that predictive equation, then, we as a juice producer could learn the pectin level and plug it into this equation and get our predicted value for the sweetness index. So if we happen to have a pectin level of, say, 250, we can put in whatever value we want to there to get our prediction. We would just compute that out. So I'm going to go ahead and just use the calculator here and compute it out. We've got 0.0023 times 250 gives us 0.575, and so we had 6.252 minus 0.575 gives us a sweetness index prediction for that particular run of 5.677. And so that's not going to be completely accurate, though. That's a best guess of what our sweetness level would be. But one of the other things that this regression analysis tells us is approximately how effective this equation is. And they tell us that with the coefficient of determination, or the R-squared value. And here we see our R-squared value is just about 23%. Technically what this means is that the level of pectin in the oranges, while it is a significant predictor of the sweetness index, only explains about 23% of the variability in the sweetness index. We could also look at our output here and see this graph, and that shows that those dots that were generated really don't fit very nicely on that line. So we would have to come up with maybe some other variables that could go into predicting that sweetness index. I want to show you one more example here on the screen that will give us a higher level for our R-squared value, and that is to use the tweets problem here. And what they've done here is they have tried to model or predict the opening weekend revenues for different films that are about to be released by looking at the average number of hourly tweets on Twitter in the week leading up to the release of that particular film. It would make sense that the more it's being tweeted about, the more likely people are going to go see it, and the higher the revenue would be. We could go to stat, regression, simple linear. Our X variable, the one that we think has an effect on the other, is the tweet rate. Our Y variable, the dependent one, is our revenues. We click compute. We can see that our formula is that Y, or our overall opening weekend revenues, would be $1.15 million plus 0.0787 times the tweet rate, or the average tweets in that week leading up to it. And here we can see on this one that the R-squared value is 82%. Just the level of tweets alone explains about 82% of the variability in those opening weekend revenues. And if we were to look at the graph by clicking on the little arrow down here, you can see that most of those dots, except for the ones that were very, very high, but most of those dots, especially down here towards the left, line up very, very well with that predicted line.